Welcome. While we are solving Gauss's law, we start out with this equation of a surface integral of the electric field equaling the charge enclosed over epsilon naught. But as we begin solving this, what we really want to solve is the electric field times the area of a specific single surface A after we have chosen the correct Gaussian surface and we've chosen a correct Gaussian surface such that we only have one surface that's non-zero, and we choose the correct surface such that the dot product becomes trivial, such that we can pull the electric field out of the integral so that the integral becomes trivial, right? Everything's nice for that. And then over on this side, we might have to start worrying about how to calculate the charge enclosed, which involves integrals of rho times dv. And we might have to worry about multiple integrals of rho times dv. We're starting, of course, at some measurement 0 and going up to, right, the measurement of this surface and dividing by epsilon naught. So we might start getting a little bit worried, a little bit concerned about what these areas are, what these dv's are. So we want to address that in this video. We, in fact, only have two shapes we have to worry about for Gauss's law: spheres and cylinders. So let's look at spheres first. Here I've got a handy example of a sphere. So our sphere has a volume of our sphere is 4/3 pi r cubed, and the area of our sphere is 4 pi r squared. Certain calculus classes will ask you to derive this, but that's fine. We don't really care, other than we know now that we want this area of this sphere, 4 pi r squared, and we can use it right here when we are using a sphere. How do we find this dv, though? Well, I can take the derivative of v with respect to any variable. If I take it with respect to any variable other than r cubed, I get nothing because there's nothing else that it depends upon. So if I do dv dr, though, I start out with 4/3 pi, and then it's the derivative of r cubed, which is 3r squared, which we can look up. And so now I have that dv dr is just 4 pi r squared. Pretty interesting. Now, one last thing, if I want to solve for dv, then I can do an old physics trick of treating dv dr as a actual ratio. This works in physics because dv is actually a small piece of volume, dr is a small piece of radius. It's not necessarily an operation that I can then say that my dv is then 4 pi r squared dr. In math, sometimes our numbers don't actually mean things, and so some mathematicians may get a little bit antsy at that kind of stuff. So that is what is going on for our spheres. We'll draw a nice little sphere just so we all feel comfortable with it. That we have some radius in the sphere. Our other possible Gaussian surface is a cylinder. So for our cylinders, we can do cylinders in two ways. They have now two different dimensions. So they have a height z, and they have a two-dimensional radius, capital R. So for our cylinders, the volume of a cylinder is pi capital R squared z, and the area of our cylinder is 2 pi r z. For the tube. For the cap, and we have two different caps, each cap is going to be pi r squared. And so then the area of our total cylinder is going to be 2 pi r z plus pi r squared plus pi r squared. But we don't care about that because if we do Gauss's law, it's only going to be one of these single surfaces. So it's either going to be a cap or it's going to be a tube, depending on which one we're going to use. And either of these is going to go as our area that we use for. But now that we have two different variables, we can now take derivatives in two different ways. So if our r is our variable, if we are building things up by adding more and more tubes, then we would do dv of our cylinder d capital R. And so we get pi r squared, derivative of r squared is 2r, so we could do 2 pi r z. And then we can do the exact same trick here, where we just multiply by this. And so we can get dvc is 2 pi r z dr for r as our variable. If we instead have the z as our variable, then we would do dv of our cylinder dz, and we would get pi r squared. And so then the dv of our cylinder is pi r squared dz for z as the variable. So these are the three dv's that we need for Gauss's law. These are the three areas that we need for Gauss's law, and we don't need any others, and so now we have them in one video.